T2 demos. T2 demos. T2 demos. This is the first test to try to do time-lapse with the X-T4. There's the parameters. We're going 300 times. Speed up, these are JPEG frames. There's lots of problems with this, but it's fairly encouraging. I'm worried, since this is just one power zone, I'm worried about when we get to like 9 power zones, whether there's going to be enough res. But we'll see in the second demo where I do some camera projector automation, I'm calling it, that it looks pretty good. We can push from here, we can push all the way into a single tile after the fact and still like read the text, for example, which was not really true with the previous solutions. I don't know if that will still be true with 9 power zones, but we'll see. So this was a big update of almost everything, because I hadn't had this grid fired up for quite some time. I'd been working on the single ring, and then obviously just doing a Hugene run, which I wanted to run until it settled one way or the other all by itself, but I didn't really understand how the Fuji X-T4 works, and its battery died. So that's where this simulation ends. All right, so here we are pushed into a single video, also with a little bit of color grading, since the background of the CDM menus really should be brown. And the LCDs we're using are really so low quality. So I just tried to get this to approximate, to sort of emphasize rendering what passes for true colors on the LCDs, and let the the T2 tile cases and the surrounding environment and stuff go hang. But I'm also, and this is using the Kdenlive transform effect with keyframes that are set to smooth, which is cubic splines, I think, and I'm starting to get them working. You can see that this is actually fairly smooth, and it doesn't have a lot of changing in directions that don't make a certain amount of sense given the action on the screen. So this is it. This is the first test. I've now got an order that connects to a charger so that it's not relying on USB power. So hopefully we'll be able to do much longer. Lots more stuff to do. Just figured I'd put the first test up. That's it. Hey folks, welcome back to the Artificial Life Advanced class. We are at T-2 and counting. Check it out. This takes a while. I'll talk about it later. All that wait for space and time and grid, and then it goes fast. Yeah. So that's it. It's been 6 weeks. I had some big fun. We'll see why I picked that particular shot of molecular configuration in a couple of minutes. I have a tremendous amount of stuff. The goals for this time was proto-ancestor runs. I'm calling that what we just saw that. The proto-ancestor did not successfully have an offspring, but it ran. It did run. Publish a book. I'll talk about that just a bit at the end. Have big fun. Okay. Yes. Had some. Will we see grandchildren for the ancestor? Maybe. It's close. Okay. Lots to talk about, starting with timeline revisions. Okay, so last time we had a lot of stuff still missing, diamond cutting missing, redeploy centers missing, and so forth. As of now, redeploy centers, I'm saying we have that. In fact, there was some stuff going on that was a little bit tricky in that video. I'll talk about it, well, if not during this time, then during the live stream afterwards. And now we had the whole month of December as a simulated evolution stretch goal. We are now taking that over. Simulated evolution will not happen. Real evolution might happen if there's bugs. But we still do not have diamond cutting. That is the big got to get diamond cutting, and then finishing the ancestor code, tuning it up, making it all work. That's the last step. Then we ought to be able to be doing runs on the grid. Atomic live chain. So, back at T-9, the question was, if we're using a pocket chain to represent our digital DNA information, we have to be able to grow the loop. But the loop is closed at both ends. We can't just grow around like we could with a swap worm. So, and I made up new grow, which eventually got renamed to shapeshifter, and new grow puts out a new corner, which puts out a new side, which eventually hooks it all up. And that was, I convinced myself, was absolutely as the best you could do in principle, because there was no way for it to happen in one event. Because if you have an event window on one guy, it cannot see all the other things that would need to change. So specifically here, if we wanted to do something with this EC, it can see its whole box. It can see its neighbor to the east, but it cannot see all of its neighbor to the north. It cannot see northeast. It cannot see all its neighbor to the northwest, and so on. Similarly, if we look at this empty one down here and say, could it do something? It cannot see. You cannot see all four pockets. What are you going to do? Eventually, in November, the pin dropped. Yes, well, but what if we let the event happen on the grid? Like, instead of having a particle to grow the loop, suppose we have a field of loop growiness that can just happen like this. And from an event that's happening at this hard cell G, it can see all of the 4 pockets around it, which is what we need to make an atomic revision that it could affect 4 codons at once. And this is exactly what the diamond sequencer has been doing all along, but I never thought that that could apply sort of everywhere. And in fact, it works great. Here's an example. Event is here, and it pops out a whole new pair of empty codons, ECs. Here's another one. I call it recorner, which flips one in and out. Same thing. Once I got that, so I had to re-implement a ton of stuff to do this. It took a long time, but once I got all of that stuff going, I could really just write rules fairly quickly. And then here's the shrink rule. And with the shapeshifter, we never even got as far as shrinking. It's just too complicated and horrible. I couldn't stand to do it. Now, boom, like that. So that's what we just saw in the opening video. Those loops that we saw, they were not growing out like fingerprints like we saw earlier in the countdown. They were live. They were bouncing all over the place. Okay, getting a grip on quote and eval. The whole idea that von Neumann's original universal constructor was demonstrating was that, in order to make a copy of something, you don't have to have a smaller thing inside it. Instead, you can have a description that gets used a double use. It gets interpreted as code, and then it also gets interpreted as data and gets copied. So at one point, we need to execute the code. In the other case, we need to quote it so that we can talk about it as if it was data. And that's what, when I was originally building the diamond sequencer, the whole idea of having these 4 different functions attached to the pockets around the diamond sequencer, having those be configurable was key to this idea. Oh, and by the way, yeah, we had originally the diamond sequencer was right above the root in the center of the diamond. In this, what we just saw there, the diamond sequencer associated with the mother started to drift. It started to head east relative to the root. That's how we're getting at deploy centers. And then the functions to change. Yeah, and it also turns out that aside from the instruction chain, which is really important, the other 3, they're, at this point, I'm kind of calling them red, green, and blue, using them for more or less whatever I want. They don't have that much special functions. They have a little bit. So here we are at the diamond sequencer. We've got the white patches, the instruction stream. We've got a do in there. And when that executes, what happens? It copies itself to a different pocket, and it regrips the processor, so now it's executing over here. And that allows the do, and then what the do is, it waits, oh, yeah, I didn't say it, that there's a little gray rim around that red flag there, and that gray rim means that we've been requested to roll forward, move on to the next non-empty codon here, and that eventually happens, and the gray border goes away, and it's a copy atom that comes up. And when do sees the second atom that came right behind it, what it does is it replaces itself with the do and then says once again, roll on to the next one. And it's now the copy that starts to actually take the loop, and now we are quoted. Now the contents of the program loop are no longer being executed. They're being read by the copy process and fed into this transfer cable that's leading to the daughter. And so there it is, the daughter loader. That's the first instruction that gets passed through the line to set up the daughter to receive the rest of the program. So, and off it goes. And finally, when the copy reaches the end of its designated copy, it erases itself and regrips back to the way it was. And now the loop is being treated once again as instructions. It's being treated as code. And this is all working. It's really cool. All right. So parallel distributed processing. Yeah. So again, this is something I didn't realize immediately at first, but the way to make this all go is that we have the diamond sequencer that's running the sequencing, that's evaluating the loop. We deploy a second diamond sequencer inside the same diamond grid to represent what's going to be the daughter. And so it gets deployed, and it's set up so that its execution stream is pointing back at the thing it came from, so that whatever instruction manages to get to that pocket first, the daughter diamond sequencer will execute it, and then off we go. So here comes the daughter loader atom. I was hoping to make that originally just be a do, but it's customized enough that that was one of the cases where I cheated a little bit and made a special one just to get the daughter going. And here it is. It's now reached into the instruction pocket, and it executes. And so it again, it regrips the processor, makes a copy of itself someplace else, and it pops out one of these little looper things that pops out into a loop like that. And then here comes the copy, and it all just starts getting fed through. The field effects start making more room in the daughter. Off we go. Another crash storm. Oh, check this out. So, yeah, there it was. That was the same thing that was from the Beethoven Sonata last time. The power supply on Lotus 1 had gone bad, and the voltage that was getting fed to that the Lotus 1 tiles were seeing was like 9 volts, and it was supposed to be 12 volts. And I had to actually get rid of the debezeler so I could see the power lights around the thing. The whole thing was flickering. It was a terrible mess. I replaced the power supply with something beefier and booted the whole thing back up. And what I realized was a whole bunch of the tiles, 4 of the tiles in Lotus 1, had gotten their disks corrupted. What happened? The common data manager just discovered all the checksum errors and fed the data into them. And in fact, the uh, Lotus 1 completely healed itself, as far as I can tell, and it's running fine. I didn't re-image anything. I didn't do anything. They took care of themselves. Nice. Yeah. And finally, Publications Division report. The reason I officially take November off is because it's NaNoWriMo, National Novel Writing Month. I've been doing it for several years now. I haven't published anything. I still haven't published anything this year. I keep my streak going. But what I was working on was a book by my dad, who died in 2008. He was a philosopher. He was an ethical ethicist. And he wrote a book about a new way of thinking about ethics to make an ethics that will serve as a philosophy of life. And so I used the format that I got from Rin, one of the folks that has followed the T2 Tile project. Thank you very much. It's got the drop cap and nice fonts and all that stuff. And I've been building it all out. My best friend from 7th grade has been helping me with proofing it, doing error correction. And getting the citations cleaned up and so forth. And I'm writing a forward for the thing. I think I'm going to write an afterword as well. It's funny because the contents of this book, which I never actually really read until just the last couple of months, really gets at a bunch of the uh, bottom up, robust first, complex systems, emergent properties, all that stuff. My dad and I used to have discussions about it, and I think this book, in some small measure, reflects the arc of his thinking from the traditional view of ethics, where it's about what you're supposed to do and what society tells you to do, and you have to keep order and all that stuff, to a much more relationship networking based, person to person based on caring. And wow, that's really good. So we're titling the book "Companionate Caring: An Ethical Philosophy of Life" by Sheldon C. Ackley. This is an early possible cover. None of this is finalized yet, but very exciting. I would love to get this out in 2022, but since we got the A Life creation countdown coming in to blast off in the same time, we'll see how it actually works. And that is it. In 2 weeks, it will be T-1, as close as you can get without blasting off. And the essential #1 goal is programmed diamond cutting. I've been avoiding that, and I'm worried about the loops being all sprawled all over the place. And when we cut it, they'll tear the loops. Time to bite the bullet and face it. I would like to also finish the forward to Companionate Caring. We shall see, and have some more fun. Folks, thanks so much for coming by. I hope to see you next time. Okay, so I guess once again, Here we go. I'm going to stop the recording and I will come back around after I get the render going. Oh, we've got some folks. And then we could play around with the simulator. I've got the same run that I did those clips from. It's still there. We could play with it. So okay, so I'll be back in a couple. Guess I forgot to go back to the waiting room, huh? No, okay. The update is rendering. So once again, we make annoying uh, um, fan noises going on and off. I don't have anything specific. I mean, there's way too much to actually talk about. Well, let me just talk about one thing. Can we go here? Okay, yeah. This is the demo that was running that I used to get all those little sample shots from. Why don't we actually start a new one instead so that we can watch it a little closer? Um, and all right, so this time we will not do a fast start. So for debugging purposes, I cheat and not what we wanted. Um, and initially set the initial size of the diamond to be larger so that things get going quicker. That's actually dangerous because it just rushes out to whatever size you do. And if it runs into some other things, things can get messed up and deadlocked and all sorts of stuff like that. So in the real thing, we start out with this size, which is pretty small. Um, and furthermore, again, so we're going to deploy two. Um, we got the diamond sequencer here. That's going to be the mother's diamond sequencer. And what we want to do is we want that entire code loop plus the diamond sequencer to migrate towards one end of the cell and then copy initialize a daughter sequencer like we saw, and then make a copy of everything over there and get it all to come out so that they're just exactly pristinely all aligned so that when we cut the thing and shrink them down, they're in a perfect recursion. Each of them now is just in the position to go ahead and do it again. Uh, um, and so the way I do that is uh, when these growth steps occur, basically the root, I guess I better use the pointer, the root, which is right here at the moment, and I really should have some special render code to identify the root better. At the moment, you have to go look at up hops equals 0 and say, oh, you're the root. It's like the most important atom in the diamond grid itself, and it looks just like all the other ones, except you also see all the contact warnings all head in there because that's where the buck stops. Uh, um, and it's right under the diamond sequencer. And so what the root does, and we're going to put that under program control soon. It's got max hops. That's the size of the grid, and when it goes from 6 to 7, that's what causes a growth level, a whole new ring all the way around, 7 to 8, and so forth. And what I am doing now is, let this go again. I have a new move where the root, in addition to making the max hops bigger, swaps with the neighbor so that now everybody is all out of sequence. They thought they were 1 hop away, and in fact, whoa, now they're 2 hops away, so they have to refigure it out. And so what happens is the root is the origin of the hop count, this one-dimensional contour, this gradient of distance from the root, and it moves when the root moves, but nothing else moves. So in particular, the diamond sequencer doesn't magically follow it, and so the diamond sequencer now starts shifting position relative to the root. And so the way that the pattern that I'm using here, it's one reason why it takes a while, is I do 2 grows and then a shift, 2 cell grows and then 1 cell shift. And the reason is if I don't do 2 grows, then we never get, if I just do 1 grow and a shift and 1 grow and a shift, which is what I tried to do at first, then the direction that we're shifting into, we lose. Okay, here's a grow. And So now we've got a whole rim around here that the program loader isn't touching at all, because it's now attempting, the loops are attempting to avoid a certain distance from the edge. So when the edge gets bigger, then okay, sure, there's enough room so that we can start popping out some more, increase the size of the ring, increase the size of the program loop, and then the loader can inject more of the ancestor code into it. Uh, um, but all right, and there it is. So now the root is over here, and the diamond sequencer is off diagonal to it, and that just goes grow, grow, shift, grow, grow, shift. Now it means that the diamond has to become quite large before there's that much distance to it. And again, this is, as always, the first thing that I got to work. And given how tight the time is for our countdown, if we're going to make this launch, I'm going to see if I can stick with this. And there's our fans. So, and now here we are. The loader has gotten most of the instructions, I think, in there. But once again, just like we saw in the opening video, see now it's pinned against the. It's got no space. It couldn't even pop up here. Number one, it would be too close to the membrane, but also it's out of the target quadrant. The program load is attempting to stay in the southeast quadrant relative to the diamond sequencer, as part of it trying to keep it away from where the diamond cut is going to happen real soon now. And so, all right, so that's it. This, okay, that looks like another grow, and that should be plenty for the loader to finish loading, I would think, unless that was a shift. Might have been a shift. But you get the idea. So that, I mean, I got to get the original master picture back, where we had the move the initial code, make a copy of the code, and then cut. We're getting close. One large concern I have is, there's not a whole lot of room for a big program. How many, the instructions of the ancestor is currently like 8, 10, or something like that. And I expect it'll be probably more like 15 or 20 or something. But this architecture, oh, that's got to be plenty of room now. So we should be able to see. There we go. So the loader just dissolved itself, and now it's operating. The reset instruction is clearing out. This is another silly thing. The reset instruction followed by the bioconstruction arm. And why is this called a bioconstruction arm? I didn't mention that in the update. It's because, is this too detailed? Well, hey, it's the live stream. That's what it's for. Let's pause this. When we saw the big comeback with the little raggedy squares there, the program code in that case was ASCII, and WSW, whatever it was, big WWW, like that, and it was stored in a string. But that has a problem with cheating from the point of view of doing an artificial life implementation, because in Ulam, the contents of double quoted strings are constant. You can't change them. You can't create new strings at runtime. There's just a pool of all the constant strings that were mentioned during compile time, and you can refer to them and use them and so forth, but that's it. And as a result, the contents of strings from a big picture point of view count as physics, because they are set when the entire set of elements, the entire set of Ulam elements is compiled and can't be changed later. And that is our definition of physics as opposed to chemistry or biology. And so that program, north, west, south, south, west, 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 whatever it was, that was physics, which is not really satisfying. It's not what we want. We want, in principle, to be carrying the program with us in a way that is specified by the ancestor, but it could have been specified differently without having a whole new set of laws of physics. And that's what the biocontour, the bioconstructor arm does. It, instead of using ASCII, which takes 8 bits per character, it has a teeny tiny little reduced instruction set of more the instructions that we need. Go left, go northwest, east, south, drop lines and so forth. Pushed squeezed down to 4 bits apiece, and it's got set room for 7 instructions in a single bio ARM constructor. And so, in fact, whereas we used to have a single string constructor that had the entire program in it, now, in fact, we have to use 2 bio constructor arms, and we're going to need more because they're completely full. That's the way it works. But if we, turned on X-rays or started messing with this stuff, evolution could happen here because these bits they're being stored in RAM. They're not being stored on the disk. I mean, they are for purposes of the loader, but after the loader's done, they're being copied from mother to daughter. They will be, and on and on. So that makes me feel good because at least I, reduce the level of cheating. And the way I think about it is, you think about Legos, and there are the beautiful little classic Lego block and the half block and the little strips and so forth, and they're great. You build stuff out of classic Lego blocks, and they're great. But that now there's all these extremely special purpose parts, like the conning tower of the Millennium Falcon or something like that, that only comes in the kit for the Millennium Falcon. And that's very unsatisfying. And that's exactly the trade-off we're talking about here between physics and chemistry. The Lego brick is beautiful, low-level orthogonal physics. You make anything out of pure bricks, that's great. Anybody else could do it, and so on. The more you start using the special little Lego guy, the special little Lego airplane, special little Lego bagel, I don't know, whatever the things that they have are, the less Lego-y it is, because now you're cheating, because all the stuff that comes out of the box, that's all physics. Chemistry and biology is just what you get by putting them together. So this going to the bioconstructor was at least one little step away from conning tower on the Millennium Falcon towards a single brick that, well, we're already using 2 of them, and we'll be using more as we go along. And it's the same thing with the daughter loader, the DL, that does a lot of stuff that's quite similar to what the LX do instruction does. But time is so tight that I went ahead and have a special purpose element just to set up the daughter loader. Would rather figure out a more general way to do it, but it's not that the dog sings well. So that's where we're at. Got a little bit more time on the render. I guess unless there's any thoughts or questions, I guess I'll call it like that. Okay, and I guess if we leave the simulator running, it'll compete with the well, what the heck, we don't care. So again, this is not run, none of this has run on the grid. I haven't, in fact, the grid, I feel ashamed of this. The grid is actually powered down at the moment because I didn't really see much point in redoing, rerunning the little fingerprint loop guys that shoot out the things and then get rid of them like had been running for weeks. I mean, it was great to find the example of the I was terrified when I saw the another crash storm because it's like, oh, I don't have time for this. And then it was actually a hardware failure. I am worried that something that Lotus One, it's the oldest one, and even when I replaced the power supply for Lotus One, and I replaced it with a bigger one that has more amps, still the voltage in Lotus One is only like 11.1, 11.05, something like that, whereas the voltage in all the in Lotus 2 and 3 is like 11.56, 11.60. It's again with a nominal 12 volt. And you can dip down quite a ways and the regulators can handle it, but eventually things start messing up, and that's what happened. I am worried that maybe there's been a little solder whisker growing or something like that that's making a high resistance short, something like that, that's now sinking a whole lot of extra power, and that's why even with a beefier power supply, we're still not getting what I would rather see above 11.5 volts, aiming it for the 12-volt rail. So I don't know if there's going to be issues there or not. We shall see. But it wasn't a software problem. I am good with it at that. That's all we need to do. All right. So there comes the daughter loader is now moving through the line here. It looks like it will be able to deploy immediately. And another thing that I think is really quite fun is that you can see this. The daughter loader does not just go bzz, boom. It goes forward. It goes back. And you can see it in the opening video. That you see these little color things that are shooting back and forth, and then it arrived. And what's happening is there's a bunch of the empty codons in there. There's actually two different types. There's empty codons that want to swap down, and there's empty codons that want to swap up. And depending on what the non-empty, here comes the reset instruction, and yeah, see that same thing. It goes forward, it goes backwards, but net it goes forwards because whenever the endpoint sees an empty codon that wants to come up, it says I'm going to turn it around and send it to go down. And when the source sees an empty codon that's heading down, it turns it around to say, well, actually, no, the source wants to see an empty codon so it can replace it with the next bit of the loop to ship through. The destination wants to see a non-empty codon so it can take it and add it to the daughter's program loop. So the fact that the destination is injecting downstream empty codons and the source is consuming empty codons from the system, replacing them with non-empty codons, means that even though the thing is bouncing back and forth, it has a net flow in the direction it wants to go. And that feels unbelievably right. That feels unbelievably biological. And I have gotten to the point where the inefficiency of that bothers me not at all. It's been a long, long road to get to that point, but here we are. Okay, so we'll take one more little round here. Okay, we're good. So I will shut us down here, and I hope to see folks in 2 weeks. All right.